of the concepts that are in Chapter 1 of our stats book. We're going to take a look at standard deviation and linear transformations. Okay, so I've been talking a lot about standard deviations, and I said there was a lot to discuss with them. We have so much to discuss because, well, standard deviation is very, very big deal as far as intro to statistics is concerned. It is the most commonly used measure of spread that we have and we will use for this course after we get finished with all the building blocks, talking about how to collect data and design experiments and talking about basic probability rules, all these things that we have coming up over the next few chapters. Quite a few chapters, actually. But it is a big deal. We might seem to forget about it for a little while, but it's always there. And when we get back to doing a lot of statistics problems, maybe chapters 7, 8, 9, 10, 11, 12, we'll be using this and more. We'll be using this formula over and over and over again. So, what is standard deviation? Well, it's a nasty looking formula, but not really quite so bad. Remember, this Greek symbol just means constant addition. X sub I is you using every individual piece of data, and then within the calculation we have mean. Now, let's talk about what's going on here. What is standard deviation? It is the average distance that each piece of data is from the mean. If a number is to the left of the mean, it's a negative distance. To the right of the mean, it'll be a positive difference. Those negative and positives will cancel out a little bit, and that means that we have to do something finagling with the formula, and I'll show you, I'll talk about that for a minute. Standard deviation uses the mean in its calculation, so it is not resistant. It is only a good measure of spread if your data is normal. Again, because you're using the mean in the calculation, which is not resistant, non-normal data and outliers will strongly affect the standard deviation and basically mean it's no good. It'll be no good for data that's not normal. And the unit of measure for standard deviations are whatever the unit of measures are for your data. It is measuring spread, so the more spread out your numbers are, the larger your standard deviation will be. Degrees of freedom are n minus 1, and we actually have to calculate variance first because of our data if our data values are less than the mean, we'll get negative differences, and if our data is to the right of the mean, we'll get positive differences. So let's point our attention to this. Why do we have to find variances first? I don't have this written. It will be in your textbook. One of the big properties of standard deviation is that the differences that you get from each piece of data to the mean, all those negative and positive differences will always add up to 0. So we can't have those differences add up to 0, otherwise our formula is going to always give us an answer of 0. So we have to square those differences first. That is why we have to find variance. Now, if we're taking these horizontal distances from each piece of data to the mean, and we're having to square those, then the unit of measure of variance is whatever the data is squares. If the data is in inches, variance will be in square inches. We don't really use variance too much until much later in the book when we start combining multiple sets of data, but we do have to find variance first to work our way into standard deviation. So the sum of these differences is always 0. That's why we must square them before we add them all up. And then we divide the overall sum of these squares, by n minus 1. Well, n minus 1 is referred to as our degrees of freedom. Okay, what the heck is degrees of freedom? If I tell you that you have, this is not maybe a great example, but it's how I use it to get across degrees of freedom. Let's say that there's 4 numbers that have an average of 10. These 4 numbers are a sample from a large population. The large population we know to have an average of 10. So our sample should have an average of around 10. It will not be, sometimes less and sometimes it'll be more, but let's say that these 4 numbers have an average of 10. What are those 4 numbers? I know I'm going to add them up, and I'm going to divide by 4, but what numbers do I have? Well, degrees of freedom is n minus 1. If n minus 1, well, if I say we have 4 numbers, then that means that n is equal to 4. And n minus 1, 3 of those numbers are allowed to vary freely. They're allowed to be completely random. And randomness is a huge, huge deal when we deal with probabilities and statistics. Well, because probabilities are behind all the math of statistics, and probabilities is a study of random numbers. And if we don't have random numbers, we will not have good mathematical basis for the statistics formulas that we use. So, and there's other issues with non-bias and stuff that we'll deal with later when we actually do talk about randomness quite a bit. At any rate, 3 of these numbers can be anything. 1,000, or 100, or 1, or 15. I don't know, but 3 of the numbers, I could say anything, but as soon as I get to the last number, that last number is not allowed to vary freely. 3 of the 4, n minus 1 of the pieces of data can vary freely. However, that last one will have to be such that when you do add these up, and you do divide by 4, you do get a value of 10. That's just my idea of explaining what degrees of freedom are. Let's walk through this formula for standard deviation so you can see it worked out one time before we move on to linear transformations. By the way, I just threw a lot of stuff at you that you might see in multiple choice questions on a test. So here's some easy numbers. 1, 2, 2, and 3. You might recognize this from the previous video if you watched it. This is very symmetric. I want to be able to do this quickly in my head, so forgive the super easy example, but we're going to find the standard deviation of these 4 numbers. Standard deviation requires the use of the mean or knowing the mean, so if I add up these 4 numbers, the mean is going to be 1 and 2 is 3, 2 is 5, another 3 is 8, and 8 divided by 4 is 2. So my average for this sample set of data is going to be 2. Well, now that I know what the mean is, I can walk through this formula and just show you the structure of the formula and the fact that this fancy Greek symbol is not quite so scary. So the standard deviation of this data will be found by doing the square root of 1 over n minus 1. N is the number of pieces of data we have. So 4 minus 1 times the sum. So this Greek summation symbol is going to come in and we're going to do this. X of 1 minus the mean squared, here's the summation symbol, plus x of 2 minus the mean squared, plus x of 3 minus the mean squared, plus, with the Greek summation symbol, 3 minus the average of 2 squared. Now, I'm going to trust that we can work this off with the calculator and not actually complete this, but if you do look at these differences before they're squared, this is -1, this is 0, this is 0, that's +1. If I sum up those differences between x of I and the mean of x, I will once again get a sum of 0, and that's not just because these numbers are extremely simple and I've made them very, very symmetric to make the math easy to do in my head, but this is the standard deviation formula worked out by hand for a very, very simple example. Very powerful measure of spread, only good for bell curves, normal distributions. Unit of measure is the same as the data. Don't forget these differences add up to 0. This is your degree of freedom. Let's move on to a linear transformation. Now, voila! We got some other notes. I've got this a bit spread out. It is in high definition though, so I hope you can read these notes. Of course, if you can't, I'll be redoing this video. Linear transformations. Linear transformations, I've even heard teachers skipping this concept, and I'm sure that's perfectly fine. And but I don't like to do this because you are going to learn something called a z-score, or we're going to make a standardized test statistic. And I don't want to go into that now, but that is a formula that's used a lot in the second half of this year, and that is a linear transformation. So I think my kids need to know what that is. A linear transformation is when you change the unit of measure, and an example in science would be going from Celsius to Fahrenheit. That is a formula that requires both addition and multiplication, depending on which way you're going. Well, it's always addition multiplication. But anyway, get out a negative number. While the center and spread will change, the shape of the distribution will not. Now what I mean by that, because if I make a distribution wider, I ain't changing the shape. But we talked about left and right skewness and symmetry, bimodal, all those weird graphs. We really are going to be working with bell curves most of the time this year. But if your data is left skewed and you run it through you run the data behind it through a linear transformation, guess what? It might be more spread out or compact. It might move left or right up the number line, but it is still going to be left skewed. You can't fix that. The formulas, which you will not see on your AP Stats formula packet, are x of nu equals a plus b times the mean of x, the old mean of x. When you do a linear transformation, you don't have to run all of the numbers through the linear transformation if all I care about is, hey, what's the new mean and new standard deviation? Or what's the new median and the old IQR, or something like that. So this formula says that your new mean is found by taking your old mean and running it through the entire linear transformation. I'll do an example in a second. And actually, this is specifically written for mean, but any measure that's not spread, mean, median, and mode, Q1, Q3, max, min, any measure you care about that is not a measure of spread will run through the entire linear transformation. Standard deviation, though, is a measure of spread, and the only thing that will affect the spread of the data, I'll show you in an example in a second, you can probably look over my shoulder and see it, is your multiple, your b value. And then again, since standard variance is standard deviation squared, did I say that over there? Since standard deviation squared gives you variance, then you'll see this looks exactly the same except for my b, instead of being b to the first, now b squared. Because literally that exponent of 2 does mean squared. Variance is standard deviation squared. Okay, what else happens with a linear transformation? If you increase the mean, you're going to move the distribution up the number line. If you decrease the mean, you're going to move the distribution down the number line. If you increase the standard deviation, it's going to be more spread out, be sort of like kind of, if the bell curve looks like this, it'll be more pancaked out and flat, or might scrunch back up. Here's an example of a linear transformation. Again, very, very simple numbers just to get the idea across. We're going to run through this linear transformation. We're going to recreate or change the unit of measure for all of my data, and it's going to be done by doing 2 plus 10 times my individual pieces of old data. Don't know why I want to do this particular linear transformation, it's just as an example. So here's my data, 1, 2, 3, real simple. 3 numbers, all just 1 unit apart, so my mean is 2 and my standard deviation is 1. What would happen, and I'm going to follow order of operations here in my example, what would happen if I multiplied all my numbers by 10? Well, 10, 20, 30. Okay, well if it's 10, 20, 30, my new mean is 20, the center, and now because I multiplied by 10, my values are all 10 units apart. So, by multiplying by 10, I increased my mean by a multiple of 10. It went from 2 to 20, and I increased my standard deviation by 10. Instead of the numbers being 1 unit apart, now they're 10 units apart. Okay, that's the B part of the formula. The A part, the plus 2, what happens there? Well, my raw data goes from 12 to 22 to 32 instead of 10, 20, 30. Now, look what happened. All my values got bigger by 2, and that means my mean got bigger by 2, but they're all still 10 units apart. So when I added by 2, I did not affect the spread. What does that mean? It means any measure that's not spread, such as mean, runs through the entire linear transformation. Multiplying and adding both changed my average. However, spread, such as standard deviation, IQR, range, we're focused on standard deviation, is only affected by a multiple. Only when I multiplied by a value did my numbers get more spread out. And, before I run out of time, you do not want to run necessarily all of your data through a linear transformation. Most questions about linear transformations are only asking you to recalculate the descriptive statistics. So don't be surprised if you get a question on the test that says the data has a mean of and a standard deviation of. Here's the linear transformation. What's the new mean and new standard deviation? Don't freak out if you don't have the raw numbers, because you can still figure out what the new descriptive statistics are.